In this video, we're going to start the Chapter 18 practice problems. So, what we have in this problem is two charged spheres. So one has a charge of positive 2 coulombs, I drew it over here. The other has a charge of negative 2 coulombs over here. And then a proton, which has a charge of E, and it's positive, I put that right here. It's halfway between them. So which of the following is not zero? So let's kind of look at all of them. So the potential energy of the proton. Well, the way that you would calculate the potential energy of this proton is you would add up the potential energy due to each pair. So this proton has energy due to this one, and then it also has energy due to this one. So you would say that if you were to call this Q1, Q2, and Q3, then the potential energy of the proton would be this one, and this would be R, plus the potential energy between these two. So that's the potential energy of this one because it has potential energy due to both charges. So when you add these, you'll get 0 because over here you have a negative charge, while for Q1 you have a positive charge, and all the other numbers are the same. So potential energy is 0. So that can be related to part B here, where we learned that we can think of the amount of potential energy that a charge has as the amount of work that somebody had to do to move that charge from really far away at infinity all the way to this point here. How hard, I mean not how hard, but how much work does it take? And that work that it takes is equal, if it's external work, is equal to the change in potential energy. And when a charge is very far away, we say that it has no potential energy because it's so far away that R is infinity. You divide by infinity, you basically get 0. So that tells us that the work to move the proton to this point is also 0 because its potential energy doesn't change. When it goes from here, it doesn't have any potential energy. When it goes here, it doesn't have any potential energy. And the force on the proton, that one is not going to be 0. So the way you would figure that out, so if I draw my 3 charges again, well, this charge here is feeling a force due to this one. Those two are like charges, so it's feeling a repelling force. And then between Q2 and Q3, the proton is being attracted to that negative charge because they're unlike charges. So I drew this arrow on top, but it should go here. I just don't have room. So this means that the proton is feeling 2 forces to the right. So they do not cancel out, so that net force on the proton is not 0. Number 2. So we have an electron is moving perpendicular to the direction of the field. How much work is done on the electron? So all these types of problems you really want to visualize. So whenever we have a charge moving through a potential difference or there's a field, I like to always just draw this picture that represents a higher voltage here, a lower voltage here, and electric field always pointing towards that lower voltage. Voltage, or you can say potential, same thing. So it says that your negative charge is moving perpendicular to the direction of the field. So let's say this negative charge here is moving downward. So how much work is done on it as it moves a certain distance, downward for example, or upward, it doesn't matter. So usually to do this, you would have to calculate, well, what's the change in potential? If you were to calculate the work done by the electric field, it would be the negative change in potential energy of the charge. And the potential change in potential energy is defined as the charge Q prime, this is Q prime over here, times the potential difference. So the point is that when the field is doing work, or if you're doing work, that there has to be a potential difference through which you are carrying this charge. And in this problem, because the charge is going perpendicular to the field, all these points on this vertical line, they're all at the same potential. Another way to think about it, all these points here are at the same distance from this positive charge, from this positive plate. So all these points here are the same potential. Another way to think about it is you learn that when you have equipotential lines, that your electric field lines are always perpendicular to it. So a line perpendicular to the electric field is an equipotential line. All the points are at the same potential, which means delta V, potential difference is 0, which means the work is 0. And actually, if you go back to this one, that is another way to think about this problem. The fact that at this point right here, halfway between these two charges, the potential at this point is going to be 0. At this point right here. Because the potential due to this charge is positive, the potential due to this charge is negative, the potentials cancel out. When you're bringing the charge in from infinity, the potential at infinity is 0. So again, you're not bringing this charge through a potential difference, you have the same potential, you're not going to do any work on it.